All right, hello everybody, and welcome to the third in our deep learning series, course series. This is a Getting Started with Caffe. You may have attended the second class 2 weeks ago, which was about our digits, which is basically an interface or a wrapper for Caffe. But in this class, we're actually going to get into the details of how to use Caffe. Just a couple of notes. So feel free to ask questions in the chat window. We have a couple of our experts online to help answer those chat questions, but just please be patient because we do receive a lot of chat questions at once, and although you may not see them as they come in, we have a big influx of them, so it takes a little while to get them answered. We will be pasting or sending out the question and answer so everyone can see it. And we also record all these questions, and they'll be on a log that gets put on our deep learning course site, so you can go look through them later. We will not be doing verbal questions at the end, but feel free to ask your questions in chat. And then we also have our office hours next week, so you can come back after having taken the associated hands-on lab, and you can ask more questions then, and we'll have all our experts available there as well. At the end of this talk, a few hours later, we are actually going to send out a survey this time to everybody. It's just a quick 5-question survey to help us improve these webinars and classes as we go forward. So I'd appreciate if you could take a few minutes to fill that out and send it back to us. All right, with that, I'll turn it over to John Barker, who's going to tell us about Caffe. All right, go ahead, John.
Thanks, Mark. Hello, everyone, again. My name is John Barker. I'm a solutions architect with NVIDIA. And today, as Mark said, we're going to cover getting started with Caffe. Okay. The agenda for today, we're going to tour Caffe, an overview of what Caffe is, some of the features, how you access those features. We'll then talk about some example applications that have been built with Caffe. We'll talk about how you set Caffe up and what sort of performance you can expect. And then at the end, we'll have a preview of the hands-on lab, and we'll close with answering as many questions as we can within the hour. So, tour of Caffe. What is Caffe? Caffe is an open framework for deep learning that was developed by the Berkeley Vision and Learning Center. It is written in pure C++ and CUDA, meaning it's very fast, it's well-tested code, but it's very accessible as it has command line, Python, and MATLAB interfaces. It provides a number of tools for pre-processing data and deploying deep neural networks, as well as obviously training the networks themselves. And it also provides a number of reference models that you can use as a starting point for training your network. It provides a number of very useful tools for managing image data specifically, which we'll talk about. And it has seamless GPU acceleration. And although the project was started at the Berkeley Vision and Learning Center, it's now an open source project on GitHub. You can see the URL on the slide, and there's a large community of contributors, and there's a large number of forks for the project which add additional functionality, which over time is being pulled into the main branch. So in a very summarized way, what does Caffe do? Well, it really is an end-to-end deep learning system that's aimed at both the practitioner and the developer. It allows you to prototype networks, and that can be on a desktop system, perhaps with a commodity GPU where you train a medium-sized network, or it could even be on a system such as a laptop that doesn't have a GPU, just for working on your network design, checking that your network will train without errors. And then you can train on a more powerful system at a larger scale, perhaps accelerated with server-grade GPUs. And the same code can transfer between that prototype training stage and the training stage. And then finally, when you're happy with the performance of your model on your training data, you can deploy to a data center or even onto embedded systems. And we'll talk about every stage of this process as we go through today. So the next set of slides will talk about some of the features of Caffe, and we'll kind of step through in the order you would encounter these features as you go through the process of prototyping, training, and then deploying a network. So the first set of features are the data pre-processing and data management features. Caffe can ingest data in a number of formats. There are these LevelDB and LMDB databases, which are in some sense the preferred format because they provide very efficient loading of data into the network. You can also ingest data directly from in your main memory if you are using the C++ or the Python interfaces. There are HDF5 files on the file system. If you are using very large data sets, that can be useful, or non-imagery data. And you can actually train networks directly from raw image files, although this is less efficient than using the LevelDB or LMDB databases. There are a number of pre-processing tools. When I say tool here, I'm referring to a Linux command line binary that will be wherever you have Caffe installed. You'll see at the bottom of this slide this file path, Caffe root /build/tools. In that folder, there are a number of command line tools that allow you to do things like create these LevelDB or LMDB databases from raw images, split your data set into training and validation data, including shuffling, and generating the mean image, which you would then subtract from your data. And I think you would have seen that happening if you took the digits hands-on lab. There are a number of data transformations that you can also apply for image data, so cropping, resizing, scaling, and mirroring, some of the powerful forms of data augmentation that people use, and the mean subtraction from the generated file. So once you've processed your data, you have it in a form which Caffe is ready to ingest. You then need to define a deep neural network that you're going to train upon your data. So in Caffe, the way that deep neural networks are specified is in a text file, which follows the protobuf model format. What this is, you see a sample on the right of this chart of a single convolutional layer of a neural network, a convolutional neural network, and how it would be defined in the protobuf format in a Caffe model. So this format is a strongly typed format. It's human readable. So by strongly typed, I mean it has a specific syntax that you need to adhere to. Otherwise, the Caffe will throw an error when it ingests the format. But it's human readable, and it automatically generates and checks the Caffe code for training a network based on the architecture you define in the file. This is a format developed by Google, and it's used in Caffe both to define the network architecture itself and the training parameters. What's very nice about this way of defining a network is that there's no coding required. You can define and train a convolutional or a deep neural network in Caffe without writing a single line of code, just using the command line interface and these prototext files, which use this protobuf format for defining the network architecture and training parameters. So within that file, there are a number of things you can define. You define each of the layers that you want to be trained in your deep neural network. You also define, importantly, at the end, the loss function. And you define at the beginning of the file the input data format that the network will be expecting, because the loss function will take the output from your neural network layers as well as your ground truth labels for your supervised training. And those loss functions that are available include popular classification loss functions such as softmax with cross entropy, or hinge loss, linear regression. You can do Euclidean loss. And there are loss functions for more sophisticated problems like multi-classification, multi-class classification problems. You can define a variety of layer types, including the important ones for image problems, such as convolutional layers, pooling layers, local response normalization layers, and you can define a number of you can make use of a number of nonlinear activation functions, ReLU being a very important one. So once you have defined a network architecture and you want to now, and you've got your data ready, you want to actually train your network, the final thing you need to do is to define what is called a solver file in Caffe. The solver file is another .prototext file that uses this protobuf format that I previously mentioned. And in this file, it's actually typically a much smaller file that lists the parameters of your neural network training algorithm. So you see an example in the center of the slide here. I'll just highlight it because there's a lot on this slide. That example in the yellow circle is saying that our network is defined in this Linnet train.prototext file. We're going to have a base learning rate of 0.01, momentum of 0.9, which is another parameter of some of the neural network training algorithms, and we're going to train for a maximum number of iterations of 10,000. We're going to save our checkpoints as we train into this folder, Linnet snapshot, and we're going to use the GPU to train. So once you've defined a solver file like that, you simply pass into the network, into the Caffe command line interface, this command Caffe, train, and the solver file, and the flag for running on which GPU you want to use. And that's all there is to starting to train a network. Within this solver file, you can also choose from multiple optimization training algorithms. We've talked a little bit so far in this course about stochastic gradient descent, and we mentioned here momentum, which is a popular extension to improve performance of stochastic gradient descent, but there are also other more advanced training algorithms such as ADAGRAD and Nesterov accelerated gradients, which can just be called in the same way from the command line in Caffe. So once you start your network training, what do you see? Caffe prints its output to the standard out in Linux in your terminal, and what you see as the network trains is an update after a certain number of iterations where the performance of the network against your training data is specified. So you'll see, for example, here, train net output and a loss. That's the value of your loss function for your training data after that many iterations. And then at a typically less frequent rate, you also see the performance of your network against your validation data, and this is listed as test net output, and you see the accuracy. So this is the default output from Caffe. There's a couple of ways you can kind of make this a little more user-friendly. One is that you pipe this standard output to some other log file. You parse that log file, and then you plot using something like GNU plot. Or you can use, obviously, digits, which we heard about last week, which is a graphical interface to Caffe, which provides visualizations of this training progress. Once you've trained your deep neural network, once Caffe has completed that number of specified iterations, it will produce a binary file with the extension .caffe model. So this isn't a human readable file, it's a binary file. It's typically on the order of a couple of 100 megabytes for a modern large neural network. That file can obviously be easily shared, and I'll talk more about that in a moment. But you can easily integrate your trained models into data analytics pipelines. And there's a number of ways you can do this. You can deploy them against new data using the Caffe command line interface again, or using one of the Python or MATLAB interfaces. And you'll actually see in the hands-on lab associated with this class, you'll get the chance to see the Python interface being used to deploy a trained model against new data. And one of the very powerful things about Caffe is that these binary.caffe model files easily deploy across different hardware and operating system environments. You can transfer it to any other Caffe installation, including importing it into digits for fine-tuning. Once you've trained on one system, so you can most definitely prototype and train on one system and then deploy on another Caffe installation elsewhere. As I mentioned, these Caffe model files are fairly compact. It's a single file. Typically, if you want to share one of these files with people, they would need more information than just the Caffe model file. They'd also need to know what the model prototext file was that you used to train it, what the solver file was, the parameters for the training process, and you typically would give them a README file containing the version of Caffe and pointing them towards where they can get the .caffe model file. You would provide a license for the use of the model, because you may have used proprietary data or something in training your model, and often people provide a description of that training data as well. So on the bottom right of this chart, you see that you can package all of those things up into a single directory, and that's what typically constitutes a Caffe model. So the Caffe developers themselves host something called the Caffe Model Zoo. You'll see the URL on the chart. What this is a place where you can package up a Caffe model, as I've described there, and then share it with other Caffe users. What's very powerful about this is that you can download from the Model Zoo trained models that have been trained on data sets that you might not be able to practically handle yourself. So very, very large data sets or data sets that you don't have unrestricted access to, you can download the model that's been trained and then use them against your own data for fine-tuning or deployment. So Caffe itself, though, when you download and install it, comes with some models included that have been released by the BVLC developers themselves. So an AlexNet model, which you may have heard of, trained on ImageNet data, the regional convolutional neural network model, and a version of GoogleNet. So everything that I've mentioned up to this point can be achieved. So prototyping, training, and development of a Caffe model can be achieved without ever writing a single line of code. But there are APIs into the Caffe code, C++ API, and the Python and MATLAB interface I've mentioned. So if Caffe doesn't support a data type or a layer type or a loss function that you would like to use for your problem, you can extend the available layers and loss functions within Caffe, and that's done by extending one of the classes in either the C++ or the Python code. So on the left of this chart, the details aren't critically important but at this stage, but I've given an example of how you might add a Euclidean loss layer to Caffe using the Python interface. And then once you've added that, you can just, on the bottom right of this chart, as you see in your prototext file where you define your model architecture, you can then reference this new layer that you've created as an extension of the base layer class in Caffe. So we'll move on now to some examples to give a better feeling of, well, what can you actually do with Caffe. So First use case is kind of the canonical example. You can do classification of images. I've given URLs here to demonstrations of models trained using Caffe and references for associated papers. We see the kind of canonical object classification. So we have the obligatory cat detection. And that's actually that example, the code to reproduce that example is included with Caffe in the file path shown. We have scene classification, so in this case classifying an outdoor scene and classifying that it has skyscrapers and office buildings, or style classification, which is an interesting application, ethereal versus melancholy images. But Caffe goes beyond just the classification of the predominant object in an image. You can also do localization of numerous images, numerous objects within an image. So here we see this image of a man riding a fish bike, and we might be able to detect that there's a face, there's a man, there's a bicycle, there's a fish, and we would like to localize all of those in the image. Well, there is a model called region-based convolutional neural networks, and there's a URL to a fork of Caffe which provides the code for fast region-based convolutional neural networks. And essentially the way this works is that you have a traditional convolutional neural network that performs your object detection. So it just detects which objects are in the scenes. And simultaneously you have another method which produces candidate locations for where these objects are in the scene, and together they go into a new type of layer in the neural network called a region of interest pooling layer, which attempts to refine those candidate object regions along with the object detections, and your output at the end of this network is both a softmax classifier giving you the probability of the presence of different objects, but also the output of a regressor which has tried to appropriately size those bounding boxes for where the objects are in the image. Caffe can also be trained to produce pixel level classification and segmentation of images. So in this case, it's a convolutional neural network where the final output is an upscale. You take your final fully connected layer, which maybe in this example has 21 output neurons, and you upscale that to be the same size as your input image, and you make a pixel-wise prediction of what is at each pixel. Again, there's a fork of Caffe which offers this functionality, and a reference that you can see on the slide. There's a great deal of interest currently in the deep learning research community in sequence learning. So that is data which has a temporal component where the sequential changes in the data provide additional information that helps you classify the data or predict what the next thing you will see is. There are, again, is a pull request to add support to Caffe for recurrent neural networks and long short-term memory networks, which are two popular approaches to sequence learning, and this can be applied to video, language, or dynamic data. So an example on the right here is that you can use, on the top you see an example where you're using a sequence of frames from a video to make a classification of what the activity that's seen in the video. And on the bottom you see an example where the input is still an image, but you actually use the recurrent network to generate a sequence of text that best labels the image. And one very powerful feature of Caffe that's enabled by its compact method for outputting the trained models and specifying model formats is an application called transfer learning. What transfer learning is where you have one network that you've trained on one set of data, a large data, for example, you've trained a network on the ImageNet data set to do object classification. You can take the weights that have been learned for that network and you can change the input data layer and the output classification task and then fine-tune the network on a new data set. And there are two things that this enables. One is you can often achieve better performance on your new data set than you would be able to if you had just trained from scratch. Second, you may be able to achieve performance on your new data set which you wouldn't have been able to achieve if you had trained a brand new neural network because you didn't have enough training data. So a good example of this being put into practice, the Kaggle data science competition platform had a competition to build a algorithm that could classify dog versus cat images. One competitor took a pre-trained network from Caffe, did exactly what I said, modified the input so that it would accept the dog-cat images and changed the output to a two-class classifier, and then fine-tuned the network, and they were able to achieve a top 10 result in that competition in 10 minutes by exploiting this pre-trained network. How do you do this in Caffe? Well, it's really just a change in a few lines of the model prototext file. You take your pre-trained.caffe model file, and then in the prototext file, any of the layers where you change the name from what was used when you originally trained the Caffe model file. So in this case, we changed the layer name FC8 to FC8dogcat. Then when you call Caffe train, that layer will be fine-tuned, will be replaced with a new layer and fine-tuned. Okay, so Caffe setup and performance. So Caffe is tried and tested by BVLC on Ubuntu 14.4 and 12.04 and on OS X 10.8 plus. It's certainly been demonstrated in numerous times by many people to also compile on Red Hat Enterprise Linux, Fedora, CentOS. And so you can download the source from the GitHub page shown here, and essentially the setup process, which is outlined clearly on the Caffe website, is to install a number of prerequisites. These include Linux applications and libraries, as well as some Python libraries. Then you install CUDA and cuDNN if you want to take advantage of GPU acceleration, and then you compile Caffe from source using make. There is an unofficial 64-bit Windows port of Caffe, but that's not supported by BVLC. So how do you leverage GPU acceleration within Caffe? Well, this is completely transparent to the user. You provide the Caffe command line utility, which I showed earlier for training a network, this GPU flag where the N in -GPU N is the device ID of the GPU if you have multiple GPUs in your system. Or alternatively, in the solver file, you specify a solver mode to be GPU. And there's a huge benefit in using GPUs within Caffe to accelerate training. Recent testing that we've conducted here internally at NVIDIA showed that on a highly performant CPU-based system with 16 cores available and making use of multi-threading, we were able to train 20 iterations of the CaffeNet model, which is very close to AlexNet, if you're familiar with AlexNet, on 256 by 256 images with a batch size of 256 images, and that took about 163 seconds. On a single K40 GPU on the same system with cuDNN version 3 release candidate, we got a 10-fold improvement in that training time. I mentioned cuDNN. I think we talked about this in the Introduction to Deep Learning module a little bit. cuDNN is an optional plugin library that's supported by Caffe and released by NVIDIA that accelerates some of the most computationally intensive elements of training a deep neural network, in particular the convolution operation and the activation operations. The latest version of cuDNN, version 3, can be used within Caffe, and here we see that going from cuDNN version 3, going to cuDNN version 3 from cuDNN version 2, you can see significant improvement in both training time of models and also on that particular convolution operation for a variety of different convolutional filter sizes. To use Caffe within, to use cuDNN within Caffe is very easy. Drop-in support. Before you compile the Caffe from source, you install cuDNN, which is essentially a process of copying a number of library files into your CUDA directory. In the make file, which the make application uses to compile Caffe, you set this use cuDNN flag to 1, and then cuDNN will be used whenever you train a network that requires one of its functions. There's no specification you need to make at actual network training time. I previously mentioned that these Caffe models, once trained, are quite compact and that they can be easily transferred to different hardware and software, hardware and operating system environments. One good example of this is the NVIDIA Jetson TK1, which is a mobile GPU-based development platform. You can take a Caffe model that you've trained maybe in your data center, maybe on your laptop, maybe in on your workstation, and you can copy that Caffe model file across to your Jetson TK1, where you have Caffe running in the Linux installed on the Jetson, and you can get, for AlexNet applied to images for inference, you can get inference at about at least 35 milliseconds per image with no need to change your code. It's a very straightforward deployment. So that's all the technical content I was going to cover in this class. There's a good amount of time left for questions, and I see we've had many questions that I'll go over. Before I do that, there is a preview of the hands-on lab, which is available now at the URL shown at the top of this chart. In this lab, you're going to see the data pre-processing tools used from the command line to prepare an image data set for ingestion into Caffe. You're going to edit a network definition and solve a file, and then train a model using the Caffe command line interface. You'll then find that there are some improvements that you could potentially make for to your trained network to achieve better performance in that classification task. So you'll modify the network definition in a number of different ways and retrain. You'll see how you can get visualizations out of the Python interface to Caffe, and you'll actually see how you can deploy a model using the Python interface to a new data set. To use the hands-on lab, go to nvidia.quicklab.com, create an account, go to the Getting Started with Caffe lab at the URL I mentioned before, and start the lab. You will be this lab will be running in the cloud, but it will provide you NVIDIA GPU acceleration, so you can train a moderate-sized network on real images in a couple of minutes while you do the lab, and it's free until the end of this deep learning course. As you may have attended, we've had 2 classes so far, an Introduction to Deep Learning and Getting Started with Digits. Both the recordings of those and the slides and the Q&As are available online at the URL. I'll now switch over to start answering some of your questions. So there was one question. I used the term earlier, server-grade GPUs. That's in reference, for deep learning, that's specifically in reference to our Tesla line of server-grade GPUs, which you can find at, I'll paste the URL into the chat window. Find details of those GPUs here. Another question was, in practice, people use more Theano or Caffe or some other frameworks. I think the question there is, which of these frameworks are most popular? The answer is, yeah, it really depends on what you want to do. And because each of the frameworks has different strengths. We see a lot of usage of all of those frameworks for sure across a number of different applications. We're going to have subsequent classes that talk about Theano and Torch, so I'll concentrate today on why you might choose to use Caffe. So Caffe, as I mentioned, a great framework if you are a data science practitioner, a deep learning practitioner, you want to quickly apply a deep neural network approach without doing a lot of coding. Then you can use Caffe purely from the command line or even with digits, and you can achieve excellent performance from deep learning in your problem set without coding. But also, if you are a developer and you are specifically a developer that likes C++ or Python, then Caffe is very extensible. I would say that Caffe offers very strong support for image data. As we've seen, the pre-processing tools greatly simplify building your whole deep learning pipeline. So that's a great advantage of Caffe. Can I use Caffe without a GPU? Yes, you certainly can. If you can either compile Caffe with a GPU or without and still have access to the functionality without a GPU. You specify that you want to use your CPU by the same flag that you passed Caffe train to specify the GPU. Instead of doing -GPU, you do -CPU. Obviously, your performance will be much different. And I quoted some performance numbers earlier. It's reasonable to expect about a 10 times slower performance. That obviously depends on your particular CPU setup and GPU setup. There are the default compilation of Caffe will use the Atlas library. If you want to make use of a multi-core CPU system, you would replace that and use the OpenBLAST library when you compile to get access to the multi-core. Says, would CUDA help in any way in deep learning? So CUDA and cuDNN are used in a large number of deep learning applications and frameworks. All of the ones I mentioned previously, and Theano, Torch, and Caffe, make use of CUDA for providing their GPU acceleration. So that's certainly the case. Are Caffe model files going to be backward compatible as new versions of Caffe come out? That has been the case in the past, and we would expect it to be the case in the future. Obviously, I am not one of the Caffe developers, so I can't commit to that being the case because it depends on what's supported by Caffe. There is currently on-the-fly upgrade mechanisms for one of the older formats that there were changes to. So if you define your prototext file in one of the older formats, then Caffe will currently attempt to convert that to the new format before it trains. Does cuDNN require CUDA 7.5? No, cuDNN will work with CUDA 6.5 and 7.0 as well. How many single node GPUs can Caffe scale to? Can it use GPUs on multiple nodes with MPI, for example? So the multiple GPU branch of Caffe, which is the multi-GPU functionality is not currently in the main branch of Caffe. There is a multi-GPU branch. That can scale to as many GPUs as you can fit in a single node, but it currently does not scale across nodes. Can Caffe utilize depth images alongside RGB? Yeah, that's a great question. So another powerful feature of Caffe is that when you define your network prototext file, I mentioned that you have to define both the input you have to define the input data format layer. Well, you can actually define as many of those layers as you want and have them all feeding into the network that you're training. So you could certainly have an RGB image feeding in as one data input, and then a depth image feeding in as another data input, and both of those being ingested either at the first layer of the network, or if you want to try some more sophisticated network architecture, have one being fed in at the first layer and one being fed in at some other layer. It's a great question here. So if there is a pre-existing model that identifies giraffes and another that identifies horses, how do you know which one to choose if you want to transfer knowledge to identify cats? Well, there's not a simple answer to say to how you would know which of those would perform better. But what I would suggest you would do is you would take the better performing of the two on your original task and start with that one. The reason I say that is that you're not really necessarily exploiting the fact that giraffes are closer, more similar looking to cats than horses are similar looking to cats. When you do this transfer learning approach, you're extracting the lower and mid-level features of the network, and then you're retraining the upper levels and the final classifier. So what you're exploiting is the fact that across almost all visual data sets, those lower level and mid-level features that are learned turn out to be very similar. So you may find that actually between your giraffe and your horse network, there's really not too much difference if the network architecture is the same between those lower levels. But yeah, there's no easy answer to that question. I would say rule of thumb is pick the best performing model unless you think that the data that was trained on was dramatically different to what you want to deploy it against. So another question, can I deploy a trained model on an embedded system that is not a Jetson? Absolutely you can. So the model itself is just a number of large matrices of numbers. So you can get those out of the Caffe model file in various ways. You could, as I mentioned, you could deploy to any other Caffe instance you have running on some other embedded system, or you could even attempt to extract those numbers manually and use them in another framework for deploying your trained network. Does Caffe support online learning? So currently, no. At this time, Caffe uses, if I understand what you mean by continuous learning as new data comes in to update the network, at this time, Caffe uses the three optimization algorithms mentioned: stochastic gradient descent, Nesterov, accelerated gradient, and AdaGrad for learning. So between batch updates of the network, you can certainly edit the solver prototext file, change the batch size, train the rates at which you update. If you want to actually have a real-time system that's continually updating the network, given input data, you certainly could continually apply another iteration of training with your new data added each time you receive data. You'd have to be very careful about how you structured your mini batches in that case. And kind of related question, what does the shuffling tool do? The shuffling tool takes your input data and randomizes the order when you split it into training, validation, and test data sets. The reason you'd want to do this is that if you had, say, downloaded all your data from the internet and you'd started with dogs, then you had moved on to cats, then you had done giraffes and horses. If you just did a straightforward, take the first 70% of your data as training data and the final 30% as validation, then you would have only trained on dogs and cats and giraffes, and you would test against horses and your network would be bad. So by shuffling, you do what we call stratify the data set across those different classes so that your training and validation contain an equal representation of all the different classes in your data set. Are there extensive inline comments in Caffe? So the Caffe source code is open source, and there are comments. If you have a hard time interpreting any of those comments, you could reach out to the Caffe users Google group, and I'm sure they will attempt to help you understand the code. So great question here. Where can I learn how to format the database in order to correctly use Caffe? So there's documentation available through the Caffe website that describes the databases themselves and the structures that Caffe uses for representing data and layer and network layer activations. For example, you can check out the training with ImageNet example on the Caffe website, which talks about this. But depending on your level of the level of development you want to get into with Caffe, if all you want to do is make use of the databases for storing your image data and training a network, then you would never actually need to get into the details of how the database is storing those images. That remains transparent to you as it's a command line application that allows you to take your data, pre-process it, and populate the database, and then another application that allows you to train the network from the database. And related question here is what does level DB mean? So level DB is just a particular database format that Caffe accepts. I'll paste in a link to the GitHub for level DB itself. And yeah, essentially it's a database that allows you to ingest your images before being ingested into the network. There are other formats allowed for data ingestion into Caffe, as I mentioned earlier. So another one is LNDB, which is just an alternative database specification. Is local batch size defined in the solver file? You actually define your batch size in the network definition file. So this is often called something like train_val.prototext. You'll see this in the hands-on labs. And you can define separate batch sizes for training and testing in this file. For those who aren't familiar, we didn't cover the details in the class. What do I mean by batch size? This refers to the fact that when we mention that we're using stochastic gradient to descent to train these deep neural networks, that's a half-truth. We're actually using an algorithm called mini-batch gradient descent. True stochastic gradient descent processes one data input at a time through the network, but you can benefit from great speed improvements in training if you process multiple data inputs at a time, but you typically can't process your entire data set because that would be too large to fit in memory in one time. So you instead use these mini batches, which are a subset of your data. Okay. How much is the maximum number of iterations to my network? I'm not sure if that question means, is there a limit on the number of iterations? And the answer to that is no. or how many iterations should I use? And the answer to that is it depends on your problem. The right way to know is typically actually to choose some reasonable upper bound, so more iterations than you think you will need, and monitor the training process, your reduction in training error and validation error. And when you get to that sweet spot where your validation error has stopped decreasing, but your training error is still decreasing, then you stop training. Because if you go beyond, when you hit that point, you've got as much capability as the network out of the network you're going to achieve, so you've reduced underfitting as much as possible, and you're about to proceed into overfitting, where you'll start to continue to do better and better with your training data, but your validation performance will get worse. So the right way to choose the number of iterations is to monitor that performance and stop when you hit that point. One question here. I assume the nets can be accessed from a C++ based API. For sure, yep. There's a classification example that's provided with Caffe on the Caffe website. I'll just paste the URL again into the chat so you can see that. And yeah, absolutely, you can access all the layers of your network using the C++ API. Okay. So what did I mean by end-to-end deep learning? Yeah, so this isn't a well-defined term that I'm drawing from in the deep learning community. This is just a term I chose to use, and what I meant by it was that Caffe can really take you from raw data and an idea about a network you want to apply to it through pre-processing your data, defining your network, training your network, modifying and improving your network, and then deploying your network. So all of the steps that you would go through in building a deep neural network application and deploying it can be achieved within Caffe. That's what I meant by end-to-end. Okay, sorry. One question, one of the things I noticed was that it was not possible to do multivariate, multi-output regression with float outputs in Caffe. Is this really true? No, that is not true. You can have, if I understand the question correctly, you can certainly have your final layer of your network producing a multi-dimensional real-valued vector. If you, for example, used a sigmoid output layer, and then you could define a Euclidean loss function which would do a multivariate regression. Often that's not the best way to do things, though. If you don't, you may want to split your you may want to train different networks for each of your different variates, but you have the either option available with Caffe. Is it possible to define custom layers and activations and using the network? Yeah, absolutely. I had a chart on that. If you look at chart 13, yep, you can define new layers, new loss functions in the C++ or the Python interfaces, and then you can just call them as if they were one of the default Caffe layers in your prototext where you define your network architecture. Okay. Could I give a reference in using convolutional neural networks in sensor fusion? It was asked already and was promised in the lecture. So here is a reference from my colleague Julie for a paper from Stanford that is addressing that. So let me just say sensor fusion. I guess just to expand on the answer to that question, I mean, sensor fusion can mean many different things. So there are multiple ways that with Caffe that I've alluded to that you could approach sensor fusion. One important one is that you can certainly have multiple different sensors that are inputting data to the same network. And these don't even need to be both or all imagery or even something like depth, which maybe appears very close to being imagery data. You could certainly have one sensor providing imagery data, another providing just some real valued feature vector of sensor measurements it's made that's associated. Really, the sky's the limit there. I mean, you quickly get into territory where you may not have good references for good network architectures that can be applicable to those different sensor modalities, but you can certainly ingest the different data types into your model. An alternative way you might do sensor fusion is to have multiple Caffe models processing your different data sets separately and then fusing the classification outputs in a kind of decision fusion framework at the end. But Caffe can certainly support both of those approaches. Can I read images from OpenCV and send it to Caffe in memory without using files on disk? Yes, you can. You can do this either with the Python interface to OpenCV and Caffe, or you can do it with the C++ interface to OpenCV and Caffe, and you can pass them or their pixel values as an array, for example, into Caffe. What is the advantage of using a batch size greater than 1? Yeah, sorry if I didn't answer this in my question earlier. The advantage of using a batch size greater than 1 is parallelism. So the mathematics of when you input a data sample into an artificial neural network and then you activate the layers in the network in response to that data sample, you are effectively performing a matrix multiplication. Well, it turns out that if you have multiple data samples and you appropriately arrange them in together in a matrix, then you can turn that you can apply the same matrix multiplication to all of those data samples at the same time in what we call vectorized code. This is great for then parallelizing that process on the GPU, and so that's where we achieve a lot of our speed advantages in training our networks through this vectorization and parallelization of those activation functions. Okay. What is the Caffe Model Zoo? So the Caffe Model Zoo itself is just a website, and what this website gives you is access to a collection of pre-trained models that are produced both by the Caffe developers and then by third-party research groups. The real power of this, as I mentioned earlier, is that you can get access to networks which you might not have the computational resources or data to train yourself. So for example, working with the complete full resolution ImageNet data set is quite a computationally intensive task and a difficult data management task. So you can go on to the Caffe Model Zoo and you can download a network that's been trained on that data set and then use it in your own application or use it as a starting point for fine-tuning your own network weights without you having to worry about training the network. Without managing the data. Another great advantage of the Model Zoo is if you are a researcher yourself and you're going to publish a paper that makes use of Caffe model, then you can provide the model you can upload the models of the Caffe Zoo reference in your paper, and then anyone can replicate your results. Okay, so I think we have time for one more question. I'll answer a GPU-related question on the slides. I said when we did our comparison of GPU to CPU, that I had auto boost turned on the Tesla K40. What that means is this is something that's enabled by default, NVIDIA GPU boost, and it ensures that out of the box, the car will always try to achieve the best possible GPU clock and maximize performance for a given workload, power, and thermal conditions. So it controls that those parameters in response to the current conditions to maximize performance. Okay, so that's the end of the hour. We're going to have another office hours next Wednesday, where one of my colleagues will answer more questions related to the Caffe framework or coming out of the labs that you hopefully will take. You can get the recordings for this session and the slides at the URL currently shown, developer.nvidia.com/deeplearning-courses, or for the previous classes, the Intro to Deep Learning or the Digits class. And the hands-on lab is available now at nvidia.quicklab.com for you to get some hands-on experience with Caffe. I want to thank everyone again for attending this session, and I'll speak to you again soon.